In this section, we will explore the environmental issues regarding pyrolysis and incineration. As we shall see, gasification is essentially the same as incineration and creates the same kinds of problems. Pyrolysis has the potential for serious environmental problems as well. Let us start with gasification. From the standpoint of what is taking place chemically, there is little difference between starved air incineration and gasification processes wherein the producer or syngas is subsequently burnt. As such, gasification has essentially the same environmental emissions as other types of medical waste incinerators. For this reason, under US EPA regulations, gasification systems are subject to the same requirements as all other medical waste incinerators. With regards to pyrolysis, the EPA began developing requirements specific to pyrolysis when they were developing the medical waste incinerator rule. However, partly because there were very few pyrolysis systems being developed at that time, EPA put a hold on those draft regulations. As noted earlier, although the idealized pyrolysis products for pure cellulose include water, carbon dioxide, carbon monoxide, methane, hydrogen, etc., there are many pyrolysis reactions taking place. In reality, just as with incineration, the actual products depend, among others, on the temperature in which the pyrolysis is taking place, the amount of time that the waste is exposed at those temperatures, and the composition of the waste itself, which in practice is a mixture of different materials that vary at different times. In the case of fast pyrolysis, there is a lot of data on the products produced. The fast pyrolysis of wood generates high concentrations of various acids, formaldehyde, phenols, furans, etc., and lower concentrations of benzene, toluene, benzoapyrene, and other toxic and carcinogenic materials. The chemical composition of the product gas, liquid, and solid residues all depend on the operating conditions used in pyrolysis, in particular the temperature and the time, and the waste composition. For example, short exposures at slightly higher temperatures maximizes the amounts of liquids generated. Longer exposures at longer temperatures tend to produce more of a carbon-rich solid residue. And at even higher temperatures, more gases are produced and the solid residue, called a slag, is formed. Studies have shown that pyrolysis can generate dioxins and furans. One study showed that even at oxygen concentrations lower than 2%, considerable amounts of highly toxic polychlorinated dioxins and furans were formed. In another study using household waste, even though the levels of dioxins were lower, the levels of furans were higher and the net result was a higher toxicity equivalent. As mentioned earlier, the product gases from pyrolysis and gasification have a certain heat content depending on the operation. For this reason, the byproduct gases are often burnt to recover energy in the form of steam, hot water, or electricity. The burning of byproduct gases is a combustion process and can therefore result in emissions of products of incomplete combustion and many of the same environmental pollutants as those found in incinerators, such as dioxins, particulates, heavy metals, and acid gases are also formed. For this very reason, the European Union classifies pyrolysis, gasification, and plasma processes as incinerators under the EU regulations. In the past, there has been a focus on air emissions, and for good reason, but it is also important to look at all output streams from any technology. For example, in the case of incineration, studies have shown that a significant percentage of dioxins released from an incinerator are actually found in the solid residue, or in the scrubber wastewater, or in the cake from the filters used to remove dioxin from the air. A review of pyrolysis and gasification systems was conducted by the British research group CADET in 1998. CADET, which stands for the Center for the Analysis and Dissemination of Demonstrated Energy Technologies, is an international information network for managers, engineers, and others interested in renewable energy and energy-saving technologies. CADET was particularly concerned about wastewater from scrubbers and boiler blowdown from pyrolysis and gasification units, and most especially the liquid residues from the chemical reduction of organic wastes from those technologies. One of the things we learned from incineration is that we need to scrutinize all output streams from technology. In one pyrolysis system I examined in the late 1990s, for example, I found that some of the air emissions were actually coming out with the wastewater through the sewer system. And so stack tests were not at all representative of all the air emissions coming out of that particular pyrolysis system. We should also consider that in all these technologies, including incineration, the air pollution control devices are mainly devices that capture and concentrate the toxic pollutants, and by doing so they simply take them out of the airstream and place them in another environmental medium, such as the scrubber wastewater or the baghouse filter, which then have to be disposed of as hazardous waste. Another issue we have to consider is that there are many pollutants that are very difficult to remove from the airstream itself, and a big example of this is mercury. It is also important for us to know how these technologies operate in the real world. When we used to do tests of incinerators, we would conduct stack tests under controlled conditions with carefully selected waste streams, and we'd control temperatures, feed rates, airflow, and so on. And many times these test results were not really representative of how these incinerators operated on a day-to-day basis. In fact, the biggest problem was that the periods which were transient, the upset conditions, were those periods when much of the pollutants were being released into the air, and these were not at all represented in many of the stack tests we did. The disadvantage with pyrolysis and gasification systems for medical waste is that there are very few of these systems around, and they haven't been around too long. And for that reason, we really do not know how these systems operate in the real world for long periods of time.